A long time ago, before there were stars, planets, or even space, there was nothing. No sky, no air, not even emptiness, just nothing. And then, in a moment we still do not fully understand, something happened. It began with a flash, an expansion, an event called the Big Bang. This was not an explosion in space. It was the beginning of space itself. There was no place for the explosion to happen. There was no before, no outside, nowhere, just this tiny beginning. Everything, matter, energy, space, and time was packed into something smaller than anything you can imagine. Smaller than an atom, smaller than a grain of sand, smaller than the smallest thing you have ever seen or thought of. It was not just small, it was beyond small. And in that moment, around 13.8 billion years ago, the universe began. Try to picture it. All the galaxies, all the stars, all the planets, even you, your body, your breath, your thoughts. Everything came from this one point. A point so small and so dense that the rules we use to understand our world do not apply. Time did not tick. Light did not shine. Atoms did not exist. There were no rules. No laws of physics yet. They were being born too. This moment was not quiet. It was not gentle. It was the hottest, most energetic moment in the history of everything. The temperatures were so high, the energy so intense, that normal matter could not form. Even the idea of temperature barely makes sense here. It was not heat as we know it. It was pure chaos. But in this chaos, something beautiful happened. The universe started to grow. Not slowly, not like a balloon in your hand. Instantly. It stretched out in all directions, faster than the speed of light. That sounds impossible. And if you are thinking of things moving through space, it is. But this was not things moving. This was space itself expanding. That growth, that rapid swelling, is what gave our universe its shape. We call it inflation. In the tiniest sliver of a second, the universe grew from smaller than a dot to something huge. Think about that. From almost nothing to something much bigger. And it happened in less time than it takes to blink. And as the universe expanded, it cooled. Just a little. But that cooling made all the difference. It allowed the first changes to happen. The first moments where the chaos began to settle. The first hints that things might become more than wild energy. That matter might take shape. But in that first instant, it was not yet matter. It was not yet anything we can touch or see. It was just energy. But that energy held within it everything that would one day become matter. The seeds of galaxies, the seeds of life, all wrapped up in that early fire. What is strange is that we know this story not from guessing, but from clues all around us. Like detectives looking at a cold case, we have pieced it together. They study the faint glow left behind by that early fire. We call it the cosmic microwave background. It is like a baby picture of the universe, still glowing after billions of years. We also recreate tiny pieces of the Big Bang in giant machines called particle accelerators. These machines smash particles together at high speeds to see what the early universe was like. It is not just theory. It is tested, observed, measured. But even with all that knowledge, the first instant is still a mystery. What caused it? Why did it happen? What came before? Those are questions we still cannot answer, because there may not have been a before. Time itself began with the Big Bang. That is hard to understand. Our minds are used to causes, to clocks ticking. But in this case, the clock started with the bang. Before that, there was no tick, no time to measure. And yet, from that no time, everything came. In just a blink, the universe had size. It had energy, it had direction, it had potential. The story of the Big Bang is not just a story of science. It is a story of origin, a story of how everything we see and feel and know came into being. It is the story of you and me and everything in between. It shows us that the universe did not begin with order. It began with strangeness, with wildness, with possibility. From that moment onward, the universe kept growing. It kept cooling. It kept changing. But the spark that lit the path was that first burst, that first impossible moment when everything began. And that is why this chapter matters. Because every breath we take, every star we see, every sound we hear, owes its existence to that first instant. And that beginning, as strange as it sounds, is something we are still a part of. In the earliest moments of the universe, time barely existed. Less than a heartbeat had passed since everything began. And already the universe was changing in ways that are almost too big to imagine. This was the era of the Great Stretch. Right after the birth of the universe, before even a full second had passed, something wild happened. The universe did not just grow. It expanded so fast and by so much that no ordinary comparison feels big enough. In less than a blink, it went from something smaller than a speck of dust to something bigger. That might sound strange, and it is, but scientists have a name for it. They call it inflation. It was so fast that it broke all the rules we are used to. Not because those rules were wrong, but because those rules did not even exist yet. The universe was writing its own rules as it grew. It is hard to picture something growing that fast, but try to imagine it like this. Think of a balloon covered in tiny wrinkles. Maybe it is crumpled in your hand. Now imagine blowing it up so quickly that in an instant all the wrinkles vanish. The surface becomes smooth and even. That is what happened to space. All its bumps and lumps were stretched out, smoothed flat by this great expansion. This smoothness is important. When we look at the sky today, far into the past using powerful telescopes, we see something strange. The universe looks the same no matter where we look. Every direction is just like every other. That would not make sense if the universe had started out messy. But it does make sense if everything was stretched and evened out in its first moments. That is what inflation did. It took whatever was there and made it uniform. But this smoothness also left tiny traces behind. Little differences, tiny bumps that inflation did not erase. Just softened. And those tiny bumps became important later. Much later. Because those small imperfections are where galaxies formed. Think about that. The stars, the galaxies, the planets, all the beauty and mystery of the night sky, all the atoms in your body, they only exist because the universe was not perfectly smooth. It was mostly smooth, but not completely. And those little flaws were the seeds of everything we see today. Without inflation, those seeds would not have existed. Without inflation, there might not be a sky filled with stars. There might not be us. This idea might seem like a guess, but scientists have ways of checking it. They look at the cosmic microwave background. That is the faint glow left over from the early universe. It fills all of space. And when we look closely at that glow, we see tiny patterns. Tiny changes in temperature, too small to notice with our eyes, but easy to spot with the right tools. Those patterns match what inflation predicts. The smoothness, the tiny bumps, the even spread of heat. It all fits. The discovery of this background light was a huge moment. It showed that the early universe was real, that it had a story we could follow. It helped turn inflation from an idea into a working theory, and that theory now helps us understand everything that came after. We know this much for sure. Inflation was fast. It was brief, but it changed everything. In the smallest fraction of a second, the universe set the stage for what it would become. The scale of it is hard to grasp. The universe did not just double in size. It did not grow by 10 or 100 times. It grew by more than a trillion times, in almost no time at all. There is no event like this anywhere else in the universe's history. Not even close. The first second held more change, more energy, more transformation than all the billions of years since. Everything that followed was built on that single moment of stretching. And yet, even though it was so short, its effects are still with us. They are in the light from ancient space, in the shape of galaxies, in the fact that the universe looks the same in every direction. Inflation is not just an old story. It is written into the fabric of space. Some of this is still mysterious. We know inflation happened. We see its fingerprints, but we do not yet know what caused it. We do not know exactly what made the universe stretch like that. We are still searching, still asking, still trying to understand the spark that lit the fire. There are ideas, there are experiments, there are clues, but the full truth is still waiting. And maybe that is part of the wonder. The mystery of a universe that began in silence expanded faster than light and left behind the beauty of stars. Inflation is one of the most powerful ideas in science. It helps explain why the universe looks the way it does, why matter is where it is, why we are here. But more than that, it is a reminder of how strange and beautiful the universe really is. It tells us that change can come in a blink, that from something tiny and wild, something vast and orderly can grow, that from almost nothing everything can appear. And so, in the tiniest moment of time, the universe stretched. And in that stretch, the future began. At the very beginning, just after the Big Bang, the universe was not just hot, it was beyond hot. It was so hot that nothing we know today could exist. Not atoms, not light, not even the rules that guide the way things move and behave. In that first instant, there were no separate forces. Everything, every kind of force in nature, was joined together into one. But as the universe expanded, it began to cool. Slowly at first, and then more. The energy that once held everything together started to drop. And just like water begins to change when it cools, turning from steam to liquid, then from liquid to ice, the single superforce began to change too. The force began to split. The first force to break away was gravity. To this day, we do not fully understand why gravity was the first to go. We know that gravity is the weakest of all the forces when it comes to tiny particles. Yet it is also the force that shapes the biggest things in the universe. It keeps planets circling stars. It keeps the moon near Earth. It holds entire galaxies together. But in the very early universe, it stepped away from the other forces. We think this happened when the universe was only a tiny fraction of a second old. After gravity separated, the universe kept cooling. Then the strong nuclear force broke away. This force may not be familiar to most of us, but it is one of the most important. It works at the heart of atoms. It glues the tiny particles called quarks together to form protons and neutrons. Later, it would also hold those protons and neutrons together inside the nucleus of atoms. Without the strong force, atoms would fall apart. The universe would have no matter, no stars, no planets, nothing solid. Next came the weak nuclear force. This force is not strong in the usual sense, but it plays a quiet, crucial role. It helps certain particles change into other particles. It is behind the process of radioactive decay, where unstable atoms release energy and transform. This decay helps power the sun. It also helped shape the balance of matter in the early universe. Without the weak force, many of the steps that led to life as we know it would not be possible. Finally, the last force to split off was electromagnetism. This is the force that creates light. It makes electricity flow. It helps atoms stick together. It guides magnets. It allows your eyes to see and your phone to work. It is one of the most familiar forces in our daily lives. But in the early universe, it was still part of that original force. Only once the universe had cooled more did electromagnetism become its own path. So now, instead of one force, the universe has 4 separate streams. Each force now had a different job. Gravity began to shape the largest structures in space. It pulled clouds of matter together until they became stars. Then stars pulled other stars into galaxies. And galaxies formed great clusters. Gravity kept everything moving in slow, steady dances. The strong force took care of the smallest places. It held the hearts of atoms together with a grip so tight that no other force could break it. It became the glue of matter. The weak force worked in hidden ways. It helped stars burn. It helped atoms change. It played a part in the birth of the elements. Its effects were quiet but powerful, and electromagnetism lit the universe. It gave birth to light. It helped atoms form. It brought color, energy, and life. But it is important to remember this. All these forces had once been one, and even now they are connected in ways we are still learning about. Scientists believe that in the future, we may find a deeper theory, one that shows how all 4 forces came from a single source, a grand idea called a unified theory. Right now, we know how the forces behave. We can measure them. We can see their effects. But the moment when they split, when the universe first cooled and began to change, is still one of the greatest mysteries in science. To study this mystery, scientists use powerful machines called particle colliders. These machines smash particles together at nearly the speed of light. For a brief instant, these collisions create the kind of heat and energy that existed in the early universe. In those moments, the forces behave differently, almost like they are trying to become one again. These experiments help us look back in time. This separation of forces shaped everything. Without it, the universe would be formless and empty. Nothing would hold together. Nothing would move. Nothing would shine. And so, in those first few moments, as the universe cooled and stretched, the deep laws of nature began to unfold. The single, strange force that once ruled all things began to step back. It handed out different tasks to different forces, and each one has been doing its job ever since. From that quiet shift came the rules that built the stars, the rules that made the atoms in your body, the rules that still shape the world you see when you look up at the night sky. In the beginning, the universe was not a place of stars or planets. It was not made of atoms or molecules. It was not quiet or calm. It was heat. It was motion. It was chaos. And it was filled with a kind of matter we cannot see today, a matter so hot, so strange that it behaved like both a liquid and a storm. We now call it Quark-Gluon Plasma, but you can think of it as the first soup of everything. This soup was not made in a pot. It was not food, but the idea is close. Imagine the thickest soup you have ever seen. Now make it hotter than anything you can imagine. Now shrink it down to a space way smaller than a grain of sand, and then let it fill the whole universe. Inside this soup were tiny particles called quarks. These are the pieces that later come together to make protons and neutrons, which then help form atoms. But at this stage, quarks were not locked inside anything. They were free, swimming, spinning, colliding, and around them flowed gluons. Gluons are the messengers. They are the glue that pulls quarks together when the time is right. But in this early soup, they were not binding anything yet. They were part of the flow, part of the motion. This soup was perfect in its way. Scientists who studied it in labs using powerful machines say it behaved like a perfect liquid. That means it flowed with almost no resistance. Nothing slowed it down. Nothing stood still. It was smooth, fast, and full of energy. But this was not the matter we know. It was something in between, something that was not yet formed, something that could shift and change in an instant. At this time, the universe was so hot that matter and energy were almost the same thing. And in this soup, particles were being born and destroyed every second. For every particle, there was an opposite, a twin made of antimatter. When a particle and its twin met, they vanished. They turned into pure energy. And then, that energy could turn back into particles again. It was a constant exchange, creation and destruction happening over and over again. The universe was like a giant kitchen, but it was not making meals. It was making reality. The ingredients were being stirred. The heat was intense. Nothing was settled. Nothing was still. This was the time when matter and energy danced together, unsure of who they would become. But the dance was not peaceful. It was violent and quick. Particles came into being and vanished in the blink of an eye. The universe had not yet chosen its shape. It was still deciding, still cooking. And in all this activity, light had no chance to shine. You see, light needs space to travel. It needs openness. But this soup was thick, so thick that light could not get through. Every time light tried to move, it hit something. A quark, a gluon, a new particle. It bounced back. It scattered. It got trapped. The universe was glowing, but it was not visible. It was completely dark to any eye. The glow could not escape. This darkness was not empty. It was full of motion, full of creation, full of change. This era, this soup stage, lasted longer than the wild flashes before it. The universe had grown from a tiny dot. It had stretched and cooled just enough for this thick soup to form. And now it was taking its time. This slow simmer gave scientists a chance to study, a chance to test. Because we can still see traces of this soup today. In labs like the Large Hadron Collider, scientists try to recreate what the early universe was like. They smash heavy atoms together at almost the speed of light. For a tiny moment, they make a drop of the early universe. And what they find is that this quark-gluon soup really did exist. It behaves in just the way our theories predict. It flows like liquid. It holds heat like fire, and it disappears almost instantly. In these experiments, we see proof of the ancient kitchen. We get a glimpse of what once was. And from that glimpse, we learn how everything began. The soup did not last forever. As the universe expanded, it cooled even more. The particles began to slow down. They began to stick together. The quarks stopped swimming and started to settle. The gluons found their purpose. They began to glue the quarks into groups, into something more familiar, something solid. But that is the next chapter. For now, it is enough to know this. There was a time when matter and energy were not separate. They were part of the same ocean, a time when nothing had shape, a time when darkness was not quiet but full of motion, a time when light had no path and atoms did not exist. That time gave birth to everything we are. From the thick, hot soup of the early universe came the ingredients of stars and cells and thought. Every proton in your body once drifted through that ancient soup. Every atom of every star carries the memory of that time. The universe was not born in silence. It was born in fire, in motion, in a dance between the smallest pieces of all things. And in that dance, something new began to rise. There came a time, not long after the wild heat of the Big Bang, when the universe began to slow its pace. It was still hot, it was still busy, but the wild dance that had filled space with energy and motion was beginning to calm. This was the moment when the universe took a deep breath. Before this point, everything was fluid and formless. The tiniest parts of matter, called quarks, moved freely through space like fish swimming in a stormy sea. They slipped past each other, they collided, they bounced, they refused to stay in one place. Around them, particles called gluons raced to keep up. These gluons carried the strong force, one of the four main forces in nature. In this time, the strong force had not yet settled into its full strength. But now, the universe was cooling. Not cold, but cooler. Cooler than before. Cooler enough that change could happen. And with this change came something new. The strong force, once scattered and unfocused, began to act with more control. It reached out and began to pull quarks together. It locked them into groups. It stopped them from roaming free. This moment was quiet but important. The universe had reached a kind of pause. Like a game of musical chairs, the fast motion slowed, and the quarks had to find seats. They had to choose where to stay. They did not have long, but it was just enough time for something solid to begin. Quarks did not group at random. They came together in sets of 3. Always 3. That is the magic number. 3 quarks joined to make a proton. 3 more joined to make a neutron. These were the first real particles. The first forms of matter that would last. Particles with structure, with rules, with purpose. A proton carries a positive electric charge. A neutron has no charge at all. Both are about the same size. Both are made of quarks held tightly together by the strong force. And both became the building blocks of everything to come. At this point, the universe was only a few millionths of a second old. But already it had taken a major step. It had created things that could last, things that would not vanish the next instant, things that would form the heart of atoms, the heart of matter, the heart of stars. But even though these particles were real, they were still not calm. The universe was still incredibly hot, so hot that even though protons and neutrons existed, they could not yet come together to make atoms. They moved too fast. They crashed into each other. They broke apart. They had energy far beyond anything we see today. The heat was near 1 trillion degrees. That is not just hotter than a stove. It is hotter than the center of our sun. Much hotter. So in this time, matter had shape, but it did not yet have stability. Still, it was a turning point. Before this, everything was just energy. Nothing had form. Now, for the first time, the universe had solid pieces. Protons, neutrons, the seeds of all the matter we know today. This change did not happen all at once. It happened in waves. As the temperature dropped, more and more quarks found each other. They locked into place. The soup of the early universe thickened and then thinned. What had once been a sea of free quarks became a scattered field of tiny building blocks. Floating, waiting, cooling. Scientists today study this moment using machines called particle accelerators. These machines smash particles together at nearly the speed of light. The energy from these crashes creates a tiny flash of the early universe. Just for a moment, the quark-gluon soup returns, and then, just like before, it cools. It forms protons and neutrons again. Every time we see this, we confirm that our story of the early universe is real. Not just theory, not just imagination, but something that can be tested, seen, repeated. In that early time, matter still did not look like anything we know. There were no atoms yet, no molecules, no clouds or dust or stars, just scattered protons and neutrons, floating alone, like tiny sparks waiting to be caught. And they would be caught, but not yet. First, the universe had to cool even more. It had to slow its breathing a little longer. It had to wait for the right moment when these particles could come together, when they could form something new. That moment would come. But what matters here is this. The chaos was beginning to give way. The wild freedom of the quark soup was gone. In its place stood the first forms, the first real matter. And though they were hot, fast, and full of energy, these particles were the future. They were the start of everything we see and touch today. That is why this time matters. It was the end of the truly strange. It was the beginning of the real. From now on, the universe would have shape. It would have order. It would still be wild in many ways, but it would never again be as free and formless as it once was. From floating quarks to solid particles, the universe had taken its first steady step. And from that step, everything else would follow. The universe was still young. It had just begun. But already it had changed. The wild heat of the beginning was starting to fade. The wild rush of inflation was over. The first real particles, protons and neutrons, had settled into place. The universe was no longer a storm of energy and motion. It was still hot. It was still busy. But now it was beginning to calm. You could say the universe was taking its first breath, and as it breathed out, it cooled. Slowly. Still too hot to touch, but not nearly as wild as before. This cooling did not happen in a day. It began just a split second after the Big Bang. It started around 1/100th of a second, and lasted for about 3 minutes. In our lives, 3 minutes is nothing. But in those 3 minutes, the universe did something amazing. It began to build. Not stars, not planets, not even atoms, not yet. But the first steps toward those things. The temperature had dropped just enough to let protons and neutrons stick together. Before this, they had been too fast, too hot. They bounced off each other like children playing tag. But now, as things cooled, they started to hold on. They began to join in small groups. This moment was the birth of atomic nuclei. When a proton and a neutron came together, they formed something called deuterium. It is a type of hydrogen, a little heavier, a little more stable. Deuterium was one of the first building blocks of everything that followed. From deuterium, more things formed. Helium, mostly. A little bit of lithium, but mostly helium. This whole process is known as Big Bang nucleosynthesis. It sounds complicated, but really, it means the universe was trying to make matter, trying to put pieces together, trying to move forward, and it worked. Almost all the helium that exists today, helium in stars and gas clouds and your birthday balloons, was made during these first few minutes. Not in stars, not in labs, but right here, in the early universe. This was the first time the universe tried to build something lasting, the first time it cooked something up from its own raw ingredients. But it was not ready yet to go all the way. Even though protons and neutrons were coming together, something was still missing. Electrons were there, floating freely, full of energy, but the universe was still too hot for them to settle down. They could not join with the nuclei to form full atoms. But what it had made in those early minutes was enough. It was a recipe, a beginning, the first draft of a plan that would lead to everything else. Because with helium and hydrogen in place, the universe had the tools it needed to create stars. And stars would one day create heavier elements: carbon, oxygen, iron, gold, everything we see around us. The cooling set it all in motion. Scientists have studied this moment carefully, not just with ideas, not just with theories, but with numbers, with telescopes, with data. They measure the amounts of helium and hydrogen in the sky, in the farthest galaxies, in the oldest clouds. And what they find matches what Big Bang nucleosynthesis predicts. That is how we know this happened. We know the temperature, we know the timing, we know the outcomes. We can even recreate parts of it in labs. We can watch how particles form and combine. We can see how the universe must have worked in those early minutes. It is not just a story. It is a memory written in the stars. But even though the era was calm compared to the chaos before it, it was still not peaceful. The universe was still too hot for light to travel freely, still too dense for atoms to form. That would come later, hundreds of thousands of years later. But in these few minutes, something had shifted. The universe had taken its first real step away from fire and toward form. It had cooled just enough to begin, and that beginning was simple. Just a few light elements, just a handful of stable nuclei. But from those small beginnings, everything else would follow. Every star, every tree, every cell, every story, it all traces back to those few quiet minutes when the universe finally cooled down and began to build. For a long time after the Big Bang, the universe was not the clear and open place we see today. It was full of light, but no light could move freely. It was full of energy, but no shape or form could truly hold. It was like a thick fog that stretched in every direction. Imagine standing on top of a mountain in heavy mist. You know there is a world around you, but you cannot see it. The light is scattered. Everything is hidden. That is what the early universe was like. A glowing fog. Bright but blind. This fog lasted for hundreds of thousands of years. From the outside, if you could have seen it, the universe would have looked glowing but sealed. Inside, particles were still rushing, still colliding, still trying to find their place. The heat was still intense. Not like the heat of fire, but the kind of deep heat that stops atoms from forming, that breaks things apart before they can stay together. By this time, the building blocks were all there. The universe had protons and neutrons. It had electrons. It had the first simple nuclei, mostly hydrogen and helium. But these parts were still flying loose, still separate. Electrons, which are very light and very fast, could not slow down. The heat gave them too much energy. They were everywhere, buzzing through space like tiny sparks. And because they were free, they blocked light. Every time light tried to move, it hit an electron and scattered, over and over again. Light could not travel in a straight line. It could not carry messages. It could not show what was there. It was trapped. But the universe kept cooling. It kept expanding. Slowly, the fog began to thin. And then something happened. Something quiet. Something small, but something that changed everything. Around 260,000 years after the Big Bang, the universe reached a temperature where electrons finally began to slow down. Not all at once, but more and more often they lost enough energy to be captured. They fell into orbit around the waiting nuclei. When an electron joins a proton, they make a hydrogen atom. When electrons join helium nuclei, they make helium atoms. This was the first time complete atoms existed. This moment is called recombination. It is a strange word, but it simply means that the loose pieces of matter were coming together. They were no longer just flying on their own. They were bonding. They were settling into place. And as they did, something beautiful happened. The fog lifted. With the electrons now locked into atoms, light was no longer scattered. It could finally move in straight lines. It could stretch out across space without being stopped. For the first time in the history of the universe, light was free. This was the moment when the universe became transparent. It had always been full of light, but now that light could shine. It could travel. It could tell the story of what had come before. That light is still with us today. We call it the cosmic microwave background. It is not light we can see with our eyes. It is a soft glow that fills the sky in every direction. It is the afterglow of the first free light, and it tells us more about the early universe than anything else we have. Scientists have studied this background glow for decades. They have measured tiny differences in its temperature. They have mapped it with great detail, and from that map, they can read the story of the early universe. The story of its size, its shape, its age, its contents. This light is not just a glow, it is a memory. A message sent from the past, a record written in light, carrying the moment the universe became clear. That moment ended the long and strange era before atoms. Until then, matter had no stable form. Light had no path, there was no real structure, only energy, only motion. But now the pieces had come together. Atoms could form, light could shine, gravity could begin to pull matter into clumps. The fog was gone. The sky had opened. The stage was set. From this point forward, the universe would begin to look more and more like the one we see today. But that first moment of light, when darkness lifted and the universe became see-through, is one of the most important steps in the entire history of everything. Without it, there would be no stars, no galaxies, no eyes to see the light, no minds to wonder where it came from. But because it happened, we have a view. We have a beginning. We have a light that still travels through space, untouched, unchanged, carrying the very first clear breath of the cosmos. After the light broke free, the universe entered its quietest chapter. This was not the end of the story. It was just the next step. A deep pause, a long breath. Before this moment, the universe had been bright, hot, and full of movement. The fog had finally lifted. Light could finally travel, but there was not much to see, because there was nothing yet to shine. No stars, no galaxies, no planets, just space and silence. Scientists call this time the Dark Ages. It is not a name meant to sound dramatic. It is a name that fits, because it really was dark. No stars lit the sky, no suns burned, no fire cracked through space. What existed was simple: hydrogen, helium, atoms born from the cooling that had come before. These atoms floated, spread out across a vast and quiet space. The glow left over from the Big Bang was still there, but it was fading. It was stretched thin by the growing size of the universe. It had become soft, cold, and dim. The temperature had dropped to just a few degrees above absolute zero. That is as cold as anything in the universe can get. It is the temperature where all motion almost stops. The heat of the early universe was gone. What was left was stillness. And yet this was not the end. It was a beginning, a very slow one. Even in the silence, gravity was still working, always working, quiet but strong. Tiny pulls began to form between atoms, small attractions, gentle tugs that started to bring matter together, first into clouds, then into clumps. These clumps were not large, they were not bright, but they were the start of something big. They were the seeds of stars. But this process was not fast. It took time, millions of years. In the meantime, the universe remained dark. For us, who live in a world full of light, this idea is hard to grasp. Imagine looking up into the night sky and seeing nothing, no moon, no stars, just blackness. That was the sky of the Dark Ages. But something important was happening even in the quiet. The strange and unpredictable physics of the early universe had come to an end. No more particles popping in and out of existence. No more wild transformations. No more plasma too hot for light to move. Instead, the universe had settled into the rules we know today. Atoms were stable. Light followed clear paths. Gravity began to shape the large structures of space. In a way, you could say the universe had finally grown up. It was no longer a wild child. It had cooled down. It had calmed down. It had stepped into its long and steady adulthood. This era is hard to study, but scientists have found clues. They can trace the soft glow of the Big Bang and see how it fades during this time. They can look at distant galaxies and work backward, piecing together how they formed from those first quiet clumps. They use supercomputers to model what the early universe must have looked like, how matter moved, how it gathered, how the first stars might have formed. All of this helps us understand a time we cannot see. We also know that when the first stars were born, they would bring this darkness to an end. Their light would spread through space. It would wake the universe from its long sleep. But that had not happened yet. For now, the universe was between two worlds. It was no longer the chaos of creation, but it was not yet the world of stars and galaxies. It was a place of silence, of waiting, of potential. This calm period is one of the most important in the history of everything. It gave the universe time to settle, time to set the stage. Time to let the basic ingredients come together. Without it, stars would not have had the space to grow. Galaxies would not have had the chance to form. Planets would not have had a place to spin. Life would not have had a path to rise. The Dark Ages were not just empty, they were necessary. And in their quiet, something beautiful was beginning. Slowly, steadily, gravity was writing the next chapter. It was bringing matter together. It was shaping the future. And even though there was no light yet, the path ahead was already forming. Soon stars would ignite. Soon galaxies would spin. Soon the universe would shine. But before all that, there was this quiet night, this deep stillness, the calm after a storm of fire and light, the peace before the rise of stars, before atoms, before light had room to move. There was a time when everything we know was shaped by things we cannot see. It was not a time of planets or galaxies. It was not a time of blue skies or living things. It was a time of change, a time of fire, a time when space itself was being born. And yet, this strange early era, the one before atoms, decided everything that came after. That is why it matters. It did not last long. From the moment the Big Bang began to the birth of the first real atoms, only a few 100,000 years passed. But what happened during that time still shapes every second we live. In the first instant, the universe was pure energy. No particles yet, no space as we know it. But in that flash, something else appeared, a balance, a tension between opposites, matter and antimatter. Every piece of matter had a twin. Antimatter was the mirror, the opposite. And when they met, they vanished. They left behind light. But there was a tiny difference. For every billion pairs that destroyed each other, there was one piece of matter left over. One extra, one survivor. That leftover bit, those tiny survivors, became everything. Without that slight imbalance, the universe would have ended in a wash of empty light. No stars, no people, no questions to ask. No one knows why there was more matter than antimatter, but that small difference changed the future. And it was not the only choice the universe made. As it cooled, something else happened. The forces of nature split apart. At the beginning, there was only one force, one rule for everything. But as the heat faded, this force broke into four. Gravity, electromagnetism, the strong force, the weak force. Each one took on a job. Each one began to shape the way matter would behave. Gravity would pull things together. It would shape stars, galaxies, and the paths of planets. Electromagnetism would make light. It would bind atoms and power everything from sunbeams to lightning bolts. The strong force would hold the centers of atoms together. It would glue protons and neutrons side by side. The weak force would make particles change. It would guide the steps that helped fuel stars. These four forces were born during this strange time, and they are still with us. Every machine, every movement, every breath depends on them. As the universe continued to cool, quarks locked into place. Protons formed. Neutrons joined them. And then, in just a few minutes, some of those protons and neutrons stuck together. They made the first atomic nuclei. Hydrogen, helium, a little lithium, nothing more. No gold, no iron, no carbon, not yet. But these light elements were the starting point, the raw ingredients. Later, deep inside the first stars, these elements would be fused into heavier ones. Carbon, oxygen, nitrogen. Those heavier elements would build the molecules that make life. They would form water, rocks, air, blood. But none of that would have been possible without the light elements that came first. The recipe for stars was written in the first 3 minutes after the Big Bang, and the recipe for life was hidden inside that first draft. Even the way galaxies are spread out today goes back to that early time. Remember inflation? That wild moment when the universe stretched faster than light? That moment smoothed things out, but not completely. Tiny bumps remained, small differences in density. Over time, gravity pulled matter into those bumps. They grew, they clumped, they formed galaxies, clusters, superclusters. The shape of the universe, the way stars and galaxies are placed, is a memory of that first stretch. We see it today, We see it in maps of deep space. We see it in the glow of the cosmic microwave background. We see it in the spiral arms of galaxies. That structure came from a time before there were stars. It came from the weird era. And it is not just out there. It is in here too. Every atom in your body was touched by the physics of that early time. The hydrogen in your water, the calcium in your bones, the oxygen in your lungs. All of it began back then. All of it followed rules that were written when the universe was only seconds old. By studying that time, we learn more than facts. We learn our story. We learn why the universe has structure, why it has stars, why it has us. The early universe was strange, hot, unstable, but it was not random. It was full of patterns, full of laws, full of steps that led to everything. That is why scientists work so hard to understand it. They look back in time using telescopes. They run particle collisions in labs. They create models on computers. Each step takes us closer to those early moments, and each answer brings more wonder. The time before atoms was not just a phase, it was the foundation. It was the spark that lit the stars, the script that shaped the world, the silence before the song.